Hi, I'm Brian with Make Stuff for Fun. Welcome back. Today I want to show you some of the design details of my pyEC, a super compact electronic development system. I personally use it as a bike computer on my electric motorcycle. Let's take a look.
This is the main control layer. It's got the MCU. It also has an op amp to convert the 3.3 DAC output to 5 volts. It's got the USB, little RGB LED. It's got the user switch, reset switch, SD card. It's got a socket for a buzzer, but could also be an onboard buzzer. It's got the CAN chip, 3.3 volt voltage regulator, and it's got a 50 pin header which pins out most of the MCU pins. On the bottom of the board, we've got a couple of jumpers to bypass the op amp for the DAC. We've got a JTAG port. There's a little jumper for uploading firmware, putting the MCU into DFU mode. There's some jumpers associated with CAN, and then these are the voltage selection for the buzzer, if you want to use a 3.3 volt onboard buzzer or a 12 volt external buzzer. This is the power layer. I've decided to run my bike peripherals at 12 volts, so I always have 12 volts available. The board has a high efficiency 12 volt to 5 volt converter. It's got two high current MOSFET outputs. One of them has a flyback diode for the horn. There's several lower current MOSFETs for controlling peripherals, like a camera, turn signals, or brake light. And there's also a 12 volt accessory output that's always on. The total input is protected with one PTC fuse. On the back side, we've got the 12 volt in, which is an XT30 connector, and the two connections for the high current MOSFETs. This is the Kelly layer. It provides a set of I/O designed specifically to work with the Kelly KLS controller. There's a 12 volt to 24 volt boost converter used as the control signal for the Kelly. There's a serial interface, two DAC outputs, and a 12 volt digital output. The 12 volt output is used to select high or low speed on the Kelly. The DAC outputs could be used to control throttle or regen functions, but significant thought and care needs to be taken to use these safely. For now, they are unused until a safe control loop can be tested. I'm looking for input on how to make this safe, besides just adding a fast watchdog timer to the code. If you have any ideas for that, let me know. This is the serial layer. It provides 4 serial interfaces for connecting peripherals. There are optional RX and TX lights. I find them really helpful for debugging. You can remove them if you don't need them. I added bidirectional level shifters, and they have optional bypass resistors. Just solder on 0 ohm resistors and it'll bypass them. Since the STM32 is 5 volt tolerant on all serial connections, it's not strictly needed to have level shifters, but it doesn't hurt either. This is the battery backup layer. It's designed to charge a single lithium battery, either a LiPo pouch cell or an 18650 cell. If the 12 volt power should be disconnected, the MCU will detect it and can turn on the 5 volt switching regulator. The charge and boost circuits are mutually exclusive and never active at the same time. There's a number of capacitors on the 3.3 power bus to give the MCU time to detect the loss of 12 volt power and enable the 5 volt backup. This is the IMU layer. It has an integrated WIT motion IMU. This greatly simplifies the IMU data acquisition, and the calculations related to the IMU are offloaded to another MCU, and data is provided by serial at a specified refresh rate. The WIT Motion IMU is also able to process GPS data from an optionally connected GPS receiver. This also offloads a lot of work from the control layer. A serial port is directly connected to the IMU, so you can connect it to your FTDI adapter and configure the IMU directly. There's also some digital outputs on the IMU that are pinned out to a connector. This is the input layer. It provides 5 switch inputs and 2 ADC inputs. ADC inputs also have a ground and 5 volt provided for convenience in connecting to a throttle or potentiometer. All inputs have an optional voltage divider and debouncing capacitor. Switch debouncing can also be done in the code. This is a test layer. It allows connection to any header pin. It provides pots to the ADC inputs. It provides output for the CAN interface. It's got some LEDs and some buttons. It's a good layer to use for testing, and it can allow you to use the pyEC for any general type microcontroller project.